So a lot of times with extension events, we try and hit the latest and greatest technologies, but sometimes it's good to go back and just start with the basics and revisit some of the things that we might have forgotten with time. Especially for some of the older people like myself who've been in the business 20 years, sometimes you can forget what you learned 20 years ago. So we're going to start with some questions, and feel free to interrupt me throughout the presentation at any time. How old do you think soil testing is? I mean, do you think it's since Romans' times? Do you think the Romans did soil testing? 1776, Declaration of Independence, when you all got a bit rebellious. I was born British, so I figured if you can't beat them, join them, right? Civil War times, World War I, World War II. Later, when do you think soil testing started? How old do you think it is? Roman times, somebody said? Anybody else? 1776, I heard. No, soil testing is actually very new. It's really World War II. Since about World War II is when fertilizers became a lot more available and when soil testing really took off. All the methods we use now are only about 60, 70 years old. Okay, what holds these things in the soil? What holds phosphorus in soils? Calcium. Calcium can hold it a little bit. But most of our soils are acidic, so iron and aluminum, especially aluminum, hold phosphorus in soils. What about potassium and calcium? So these are cations. What holds cations? It's on your soil test report. Does a sandy soil hold as much potassium and calcium as a clay soil? Your cation exchange capacity, that's right. So the negative charge of the soil. So what two things make up your cation exchange capacity? Organic matter's one, and clay's the other one. So yeah. What holds nitrogen in a soil? Is that a trick question, do you think? Okay, so we know that nitrogen leaches very easily. But if I take a soil, I wash all the nitrogen out, with water, there's still a lot of nitrogen in the soil that's not leached. What form is that nitrogen in? It's in the organic form. It's almost all in the organic form. But if you take a soil and analyze the nitrogen, about 1 to 3% is in that nitrogen form. There'll be a small amount of ammonium, but most of it, 97, 99% of the nitrogen in the soil is in your organic matter. And we can test it, but when you submit soil samples, we don't test it because it's released through microbial reactions that are weather dependent, and we can't predict those. Sulfur and boron. We don't care about them, right? They're not the macronutrients. Sulfur's kind of like nitrogen. Boron's more like phosphorus. So when you start looking and reading publications about soil testing and nutrient availability, this is some of the terminology you see. You see all these vague terms like available, desorbable, bioavailable, and these kind of mean different. We all have a general idea of what they mean, but they mean slightly different things to slightly different people. As scientists, we prefer using very specific terms like malic 1 or malic 3 extractable. And what these things are trying to do is get at these. What is bioavailable? What is plant available? So what we're meaning with these extractable things, we're most interested in finding indicators of plant availability. Do we have a soil test that indicates how much the plant will take up? It doesn't necessarily measure exactly what the plant's going to take up, but it's well correlated. It'll give us an indication of that. And there are these terminologies. You can, on soil test reports, you can see pounds per acre, which can confuse people because it really doesn't mean pounds per acre. They just multiply the concentration times the number of pounds per acre of soil. But that doesn't mean that amount's going to be plant available all the time. So some characteristics. A soil test should extract all or a proportionate amount of plant available nutrients from a soil. One of the most important things is it should be accurate and rapid. I'm sure you've heard lots about soil health over the last couple of days and over the last couple of years. Most chemical extractants, malic 1, malic 3, Bray, Olson, you can do them very, very rapidly and you can do large numbers of them very rapidly. A lot of the soil health tests take a lot longer, but all of the chemical tests are very, very rapid and reproducible. And the one thing we're really looking for, it should be well correlated with plant growth and response to fertilizers. Here's a cycle. I'm sure you've seen things like this many times, but what we're doing with soil testing is we're just looking at this. We're really looking at, when you do a phosphorus extraction, you're going to look at what's in the soil solution, which is a very small amount, but really you're looking at what's absorbed on the aluminum and iron and a little bit that's with the calcium. All this organic phosphorus over here, that's about 1/3 of the phosphorus in the soil, we just kind of ignore that. We're really looking at the chemical reactions that are going on in the soil for most of our nutrients. So you already told me that nitrogen leaches very easily. Phosphorus doesn't. So if phosphorus doesn't leach, it means it's strongly held by a soil. How can phosphorus not leach and still be plant available? I mean, when the soil roots, they take up water from the soil, they take up the nitrate with that. But you keep hearing phosphorus is very strongly held by the soil and not leached. How can the plants get it? Well, there is some in the soil solution, but it's a very low concentration, and the plants can get at that. And what the soil does, it keeps that concentration very stable. The concentration of phosphorus in a soil solution is in dynamic equilibrium. Dynamic equilibrium, if you think a bottle of soda, you loosen the lid, you get that carbon dioxide coming out, you put the lid back on and shake it, it'll re-equilibrate. It'll release more carbon dioxide into the air in that bottle. So that's like the soil. The plants take the phosphorus out of soil solution, the soil will replenish it through chemical reactions. Unlike nitrogen, nitrogen's released by microbial activity. So this is what the concentration of nutrients looks like in soil. We've got nitrogen and phosphorus on here. So soil nitrogen concentration on the y-axis, months of the year along the bottom here. So what's happening here, December, January, February? Why is there so little nitrate in the soil? Sorry? Cold temperatures, so microbes aren't breaking down the organic matter, but what else happens in the winter? Are your soils dry? Winter times when you get most of your leaching occurring. So not much is produced, and what is produced can be leached because the soils are wet. And then in the spring, obviously warms up, and then it reaches a peak before it starts to drop back down again. Why does it drop? I mean, it's still warm in June and July. This is under corn. So yeah, it's crop uptake. So any of you are familiar with the PSNT, the pre-soil, pre-sidedress nitrate test? What we're doing is measuring the height of this peak before the corn starts taking all of the nitrogen up. But this is why in general we don't measure nitrogen, because it varies rapidly throughout the year, other than that very time-specific PSNT. And then later on in the year, when the corn stops taking up nitrogen, it's still warm, you get a second peak here. But look what happens with your phosphorus concentration in the soil. It's in equilibrium. There's a small amount in the soil solution, which is what this is showing, is a low concentration, but there's a lot on the soil. So the plant takes it up, it's immediately replenished by the soil. So this is why with nitrogen, we've only got that one test, the PSNT, but with the phosphorus, you can take a soil sample any time of the year. And there's a lot of phosphorus in soils. When you look at the total, there can be over 1,000 pounds per acre, but a lot of that's not plant available. So what we're doing with soil tests is just extracting a small portion of that and estimating how much is going to be plant available. So again, lots and lots of phosphorus in the soil, over 1,000 pounds per acre in most soils. About half of it or more is in inorganic forms, and that's what we measure in soil testing. We pretty much ignore the organic matter. For phosphorus, we assume the organic phosphorus is going to stay much the same year to year, because that dynamic equilibrium that keeps the soil solution concentration constant, that's all associated with the mineral part, not the organic part. So roots are very good at getting low concentrations of phosphorus in the soil. soil solution will be replenished continuously. It's called dynamic equilibrium. If you add a little bit of phosphorus to a soil, it'll immediately go into the soil solution, but then get sucked onto the soil. And the same, if you take it out of the soil solution, it'll be replenished from the soil. So how does pH affect nutrient availability? You can tell this is one of my newer slides, but this is obviously an older slide, but one of the things is, this chemistry data doesn't change with time, so you've got the amount of phosphorus versus pH. So here, there's like a valley where that's between 6 and 7, roughly where we want to keep our agricultural soils, and that's where our phosphorus is most available. If you go above that, you're going to get a lot more held by calcium, but it's really when you go below about 6 that you start getting phosphorus held very strongly by soils. First by the aluminum, and then by the iron. So why do you think the aluminum fixing of phosphorus starts dropping when you get down below about 4.5? What happens to plants in very, very low pH soils? Aluminum toxicity, that's right. So the aluminum starts to dissolve and it's taken over by the iron. So what are the general soil tests you hear about? Some of the phosphorus tests, and when they were developed, the Bray, 1945, last year of the Second World War. Mehlich 1, 1953, a bit newer. Look at Mehlich 3. We think of it as a well-established soil test. It's only about 30 years old. That's why a lot of states still use the Mehlich 1 test, because all of the recommendations were developed with Mehlich 1, and Mehlich 3 was developed after the recommendations. So they haven't had the money to redo the recommendations. And then the Olson, it's about 1954. So what's the difference between these? Look at I don't expect you to understand or care much about these exact chemical formulations, but there are a couple of important points to make. Look at the concentration of acid. This is sulfuric acid and hydrochloric acid in the Mehlich 1. Look at 0.0. Look at the Mehlich 3. There's no 0 there. So the Mehlich 3 extractant is about 10 times more acidic than the Mehlich 1 extractant. And that's very important because it means that it's not going to be, the pH is not going to be controlled as much by the soil. Most of our soils are acidic, so it doesn't matter a lot, but occasionally you have a calcareous soil or one higher in calcium, and having that stronger acid in the Mehlich 3 is really going to make a difference. It means it's more applicable across a broad range of soils. The other thing, Mehlich 1, there are only 2 acids, but Mehlich 3, there are a whole bunch of different things in here, especially this EDTA, ethylene diamine tetraacetic acid. It really gets the micronutrient side. Bray, again, low pH, fairly simple. The Olson, it's really different. You can really use any of these in our soils, our acidic soils here. This one, Olson, you really can't. Look at the pH of it, 8.5. So it's an alkali soil test. So it was developed for the calcareous soils, and it's much more applicable out west than it is in our region. Anybody have any idea what this line is and why it's important? We're talking about soil testing. Anybody any idea what that line is? What, sorry? Glaciation, that's correct. This is where the last glaciers came down to. So what does that mean for soils? What does it mean for the soils above that line versus below that line? What happens to soils under a glacier? I had a lot of fun with a graduate student asking that question. Graduate students said they just got squashed a little bit by the weight. What do you think happens under glaciers to soils? They get stripped. I mean, the glaciers are moving. There's all that weight on it. They get stripped down to bedrock. That means all of these soils up here are fairly young soils. So the soils above this line are very young. The soils below this line, which is most of this region, the soils below this line are much older. And that's very important for the clays especially. The clays we have are maybe millions of years old, whereas above this line they're tens of thousands of years old. So the older clays have a much lower cation exchange capacity. So the different soil tests that you may come across, Bray, developed in 1945, widely used in the Midwest and North Central, not as much in this region. It's well correlated with crop response, but it's really designed for high cation exchange capacity soils. And again, from that previous slide, we have low cation exchange capacity soils. So this test was not developed for this region, for high cation exchange capacity and high organic matter soils. Do we have high organic matter soils in this region? So the Bray test was not developed for this region. It was, you can use it, but it's really not what it was developed for. So I wouldn't recommend it. The fluorine in this, it complexes with the aluminum to help release phosphorus in those young soils. Not suitable for soils with high base saturation, in other words, a lot of calcium and magnesium, high pH. So not good for calcareous soils, and it really wasn't developed for our soils. Malic 1, on the other hand, developed in 1953 at NC State University, primarily used in the southeast and mid-Atlantic. Does that sound like us? It's the state soil test in Virginia still, and in many southeastern states. Best suited to acidic soils. Do we have acidic soils? Yep. Low cation exchange capacity, low organic matter. How many soils do we have above 5% organic matter? No, not a whole lot. So this is pretty well suited for our region. So it's not well suited for high cation exchange capacity, high organic matter, and calcareous soils. But we really don't have many of those soils around here. So it still works fairly well. Malic 3, on the other hand, again, when you look at the concentration of the acid, Malic 3 is about 10 times stronger. So it's going to extract more nutrients as a whole compared to the Malic 1. But because it's stronger, it's much more applicable to a wide range of soils. It's used throughout much of the US and Canada, not just in our region. It's a much improved version of Malic 1 and extracts the same nutrients. Malic 1 can't extract sulfur because there's part of the extractant is sulfuric acid. Has anybody ever asked whatever happened to Malic 2? That's the first thing I saw. I thought we got Malic 1, we got Malic 3. I mean, could he not count? He was a great chemist. But I guess the Malic 2 came out, and before anybody got to testing it much, he came out with Malic 3. So there is a Malic 2 in the textbook somewhere, but it was never really used. Malic 1 was used to develop most of our crop recommendations. After our crop recommendations were developed, Malic 3 came in, and a lot of people transferred to it, and they did regressions and so on. They didn't redo a lot of the original work. They did in a couple of instances, but most of the recommendations were still developed with Malic 1. The EDTA as well, it's a chelating agent. It's used in a lot of foliar fertilizers to keep things in solution. But in an extractant, it'll help get those micronutrients out. So it's good for micronutrients too. And of course, it's got the fluorine as well, like the Bray, to help with the phosphorus in high organic matter soils. So a great soil test. Olson, 1954, just sodium bicarbonate. If you want to do a soil test, this is the easiest one. You get a little bit of sodium bicarbonate, dissolve it in water, and away you go. The other ones you have to mix certain different things. So it's very simple. It precipitates out calcium and aluminum, but again, it's got a high pH, 8.5. It was primarily developed for calcareous soils that we don't have in this region. Water extraction. Anybody heard of the water extraction? I've heard people go on the internet and read about it and say, why don't you guys do this modern water extraction test? And it's really not a good soil test for our soils. It's used for some sandy soils in the Netherlands because they don't have a high fixing capacity, but it's really not widely used for prediction of plant available nutrients. It'll show you what's in soil solution, but it won't show how much phosphorus and so on is bound on the soil. Like we talked about the dynamic equilibrium between the solid phase and the soil solution. The water test only shows what's in the soil solution, not what's on the solid phase. Our scientists use it occasionally to show environmental losses, just like water will show how much nitrogen is going to leach. We do runoff experiments and so on, and it's fairly well correlated to how much phosphorus is lost in runoff in some situations. But it's really not good for plant availability. Sometimes you see this 0.01 molar calcium chloride. It's a very weak salt. It's basically trying to replicate the salt concentration in most soils, but it's similar to the water extraction. So So this is where some people use the water extractable. So here we have leaching of phosphorus versus water-soluble phosphorus. Yeah, we can use it for correlations like that, but in terms of plant availability, it's pretty useless. So if we replace the x-axis, so here we have water-soluble on the x-axis, leaching phosphorus on the y. All we're going to do is change the x-axis from water-soluble to Mehlich 3, and you get these like little change point things where leachate phosphorus, it goes up, and then the soil gets saturated with phosphorus and starts going up faster. So when you look at regulations, a lot of soils have a soil test phosphorus cap, and that's why it's in there. Like in Virginia, we have an environmental threshold of 65% saturation based on the Mehlich 1 soil test, because we figured above that, phosphorus leaching and runoff is going to increase dramatically. And there's no agronomic reason for it. So converting between some soil tests, most of you are probably aware you can do it. Everybody's got their own favorite equation, converting from Mehlich 1 to Mehlich 3. You can do it, but it's not very, very accurate. South Carolina, here's their equation. Mehlich 3 phosphorus equals 1.5 times Mehlich 1 plus 10.8. And when you look at their correlation, it's about 0.9, which means it's explaining 90% of the variability. North America Proficiency Testing Lab, they're across the US. They've got their equation. Look how much different it is. Mehlich 3 equals about 1 times Mehlich phosphorus plus 19. And it only explains about half of the variability. Why do you think it's so much better in South Carolina than for across America? Do you think the soils might vary a little more across the country than they do in South Carolina? So they've got some of those newer soils up in the Midwest in this data, but not in this data. So there are equations to convert between them, but they're not very accurate. And it's all due to this variability in soil properties. So here's some of these correlations. So here we've got Olsen phosphorus versus Bray. A little bit of scatter, but you can see they've got a line through the middle of it. Mehlich 3 versus Bray. And what they've done here is they've broken it into low pH soils, well, low, relatively speaking, below 7.3, or soils that are higher pH. And you can really see this Bray test, it really doesn't do well in the high pH soils. But if you look at the correlations, so here we have Bray versus Mehlich. If you look at a value of, say you've got a value of 20 for Bray, that means for Mehlich 3 you've got anywhere between about, what's that? So if you go up from 20, you've got maybe about anywhere between 15 and about 30. So you can do these conversions, but they're not perfect by any means. Some more questions. It's early in the morning, but just checking you're not asleep yet. These are some of the questions. I supervise the soil testing lab at Virginia Tech, and these are some of the questions we get. Last year, my soil had 55 parts per million phosphorus. This year, it was 70 parts per million after I didn't fertilize. If I didn't fertilize, how can my soil test go up? What's wrong with you guys? What's wrong with your soil testing? What do you think?
Timing of the test.
The what, sorry?
The timing of the test.
The timing of the test? No, not the timing of the test. Soil test phosphorus stays fairly consistent throughout the year. And even if the soil is wet, we dry it before we analyze. Where does the biggest error in soil testing occur? Depth of the soil test, that's exactly right. When you fertilize, phosphorus is held fairly strongly by the soil, so it's going to stay near the soil surface. So if you take a deeper soil test, you're going to be diluting it a little bit more. It's the consistency of the depth. And across the field, do you think or a backyard, do you think phosphorus is going to vary a little bit? So there's a lot of variability with soil testing. When you submit it to our soils lab, we're very good at getting the same number over and over again. It's the soil sampling where the biggest error is. So to follow up on that, it's dry this year and hard to get down to 6 inches. I don't want to break my soil test probe. Is 4 inches enough? What do you think? Well, do you think it might be related to this a little bit? So you do a slightly different depth, it's going to change it a little bit. If you follow the recommendations for your sampling depth, there's a little bit of insurance in the recommendations. So if you can't get done, if it says 4 to 6 inches, and you take a 4-inch sample one year and a 6-inch sample the next, it's going to vary your report a little bit, but there's insurance fertility in there to make sure that you're not going to get those yellow-looking areas or poorly growing plants. In our soil testing recommendations, they found the critical level where plants normally have enough, and then they added a little bit of insurance to make sure that because of variability across the field, because of variability in collecting samples, you're going to have enough, so there is a bit of fertility insurance in there. What is variability? What are the sources? We talked about sampling depth. Anybody have any other ideas what causes variability? Anybody seen an aerial photograph of dairy manure application where they go out and paint the field with dairy manure? Some places overlap. Some places he runs out and has to drive back to the pit and can't be bothered to go into that side of the field. So there's variability in fertilizer applications. Out here, I guess all of our fields are pretty flat, but are they flat everywhere? Do you think topography has a little bit? So if you have a field that's sloping a little bit, you might get a little soil erosion, and then in the flat bit, a lot of that soil can sediment out. So you get differences in texture. There are a lot of reasons for variability. We know across fields we get better yields in some part of fields than others. If I go out to a field and I know that this part of the field has a good growing corn crop and this part doesn't have as good a corn crop on most years, where do you think the soil test would be higher? It might be counterintuitive. You look at the good corn and say, well, it must be higher there. That's why the corn's growing well. But you actually generally find that it's in the worse areas the soil test is high because the farmer treats it as one field. He does a nutrient application across the whole field. And where the soil's better, it holds more moisture, you get a better growing crop. And where you get less crop, because you're not taking as much out with the crop, the soil test's a little bit higher. So how many subsamples? You're meant to walk across a field and take a bunch of subsamples, mix them all together, submit one sample. How many subsamples should you take for one representative sample? 12 to 15. Sorry? 12 to 15. I think our recommendations are 10, but yeah, you need a lot. You can't just go out and take 3 or 4 and say that's enough. What about if you've got bigger fields? How many samples should you take per acre in a 10-acre field? I think our recommendations are about 5. So you'd really need, again, I can't say it too much if you're looking at mistakes in soil testing, anything from where you take the sample to getting the recommendation. The biggest error is in this collection of the sample. You really need to spend the extra time to get a representative sample. So what's the scale-up factor? So you submit a soil sample from soil testing. So you send in maybe half a pound of soil. How many pounds of soil? We test that. We only actually test about 5 grams of it. So what's the scale-up factor? How many pounds of soil are there per acre? 2 million pounds. Got a well-educated audience here. So there's a huge scale-up factor between what you send to us and what's in the field. So if you don't sample that field thoroughly, the recommendation's not going to be accurate either. Got some work out of the Shenandoah Valley. You've probably heard a lot about high phosphorus testing soils. How much phosphorus does it take to build up soils? How much does it take to draw the phosphorus back down again? So this is from the Shenandoah Valley. We had 3 sites. So the soils are a little heavier than they are down here on the coastal plain, obviously. So the soils here, is the soil test phosphorus going to change faster on a sandy soil or a heavy soil? Sandy. It's going to change much more quickly in a sandy soil. So take that into account when you're looking at these results. It's going to take more phosphorus to change the soil test phosphorus on these soils than on the soils here. So my predecessor started this work. I finished it up. They had all these different treatments, no phosphorus added. And every year they grew corn. They fertilized with nitrogen. But it's really the phosphorus that was different in between these treatments. No phosphorus. So you'd expect with time the phosphorus is going to go down. N-based litter, so nitrogen-based litter applications are over-applying phosphorus. Phosphorus is going to go up. And then P-based litter, which is trying to match what you put on and what you take off. And he had these with and without chemical fertilizer. I mean, the chemical fertilizer one was the same rate as the litter, and it was basically the same. It didn't matter if the nutrients came from poultry litter or chemical fertilizer. But so just to make it a little easier, I'm only going to present data from these 3 treatments. So it was continued for 7 years. Soil test P was always sufficient. So these were high soil test phosphorus fields. They didn't need phosphorus according to the soil test, so it wasn't going to limit crop yield at all. Mostly corn silage. These are on farmers' fields. There was some hay in the rotation occasionally some grain, but mostly corn because it was on dairy farms. Yields across treatments were all the same. So these treatments, different nutrient applications, the same nitrogen. It didn't matter how much phosphorus you applied because phosphorus is sufficient. So it's just what happened to the soils. So when we looked after 7 years, here's a site in Rockingham County. When you looked at the no phosphorus treatment, they'd mined 364 pounds of phosphorus out after 7 years. You compare that to the nitrogen-based litter application, they'd applied 618 pounds more phosphorus than they'd taken out. When you look at the change in soil test phosphorus, obviously a very high soil, 55 parts per million is our cutoff where we say you don't need any more, and it's up around 700. So when you look at the difference, either mining 364 or adding 618, that's a difference of 983 pounds, and it had changed your soil test phosphorus by 55 parts per million. You can see here where it's being mined, it was down 43, and where they'd over-applied, it was up about 12. So it took almost half a ton of phosphate to change the soil test by 55 parts per million. So I got 3 of these tables. Next one is in Page County. Again, no phosphorus applied. After 7 years, they'd mined 447 pounds. Nitrogen-based litter, they'd applied 376 more than they'd taken off in the crop. You can see the Malic 1 phosphorus level. It had either gone down by 20 or up by 34. So when you compare it, a difference of 823 pounds of phosphate over 7 years, it had changed the Malic 1 by only 59 parts per million. Third site, similar story. You'd either mined 419 or applied 783 more, a difference of over half a ton of phosphate per acre, and it only changed it by about 53 parts per million. So when you look at the 3 sites, the mass balance, the change in Malic 1 phosphorus, how many pounds of phosphorus does it take to change your soil test phosphorus? Well, for Malic 1, to change Malic 1 by 1 ppm, it was between 14, 18, 23. On average, it was about 18 pounds of phosphate to change your soil test by 1 ppm. For Malic 3, because Malic 3 extracts more phosphorus, again, conversions aren't perfect, but it takes less phosphorus to change Malic 3 by 1 ppm. But you're looking at about 12 pounds to change Malic 3 by 1 ppm. So what does this mean for our really high soil test phosphorus soils? Like in Virginia, 55 is enough. If you're up at 500, how long is it going to take to get your soil test phosphorus back down again?
A lot of years.
A lot of years with no phosphorus fertility. Okay, so changing gears a little bit, I supervise the soil testing lab. These are the boxes, examples of some of the boxes that come into the lab. We got the good, the bad, and the ugly here. So here we have a nice soil test box. There's a fill line on it. We tell you not to fill the soil test box up to the top. And the first thing we do, we open the box, we put it in an oven to dry. This person, they're trying to be thorough. They figure we send more soil in, then you're going to get a better result, right? So you can see it's flat on top. They've pushed that soil down into the box. They figure more soil, better result. Well, what do you think would happen if we put this in an oven? Is it going to dry? So you send in more soil. We've got to start flicking some of the soil out and loosening it up a little bit. Any comments on this one? First we smell.
A year like this.
Sorry?
What else you do in a year like this?
What else do you do in a year like this? Well, the first thing we did was smell it to check it was soil. Then what happens, do you think, with the clay soil? You take a clay soil that's very wet like that and you put it in an oven to dry. And you turn up with a clay brick. So, I mean, in a year like this, yeah, it is a little bit harder, but try not to send sloppy soil sap. We do dry the soils, but if you get a heavy rain, at least try and wait a couple of days for it to dry out a little bit. Don't send stuff like this in. It makes our lives very difficult. So here's in our soil testing lab, which is similar to other soil testing labs and how they do things. So you can see the diversity in the soils, but you see two boxes here that have the lids closed. Any idea what those are? Yeah, there are checks. There are quality control samples. So every time we run a tray of samples, there are two checks. They check that 0 really is 0, and then there's a standard in there that varies between boxes or varies between trays. And it just checks that all of our instrumentation is working. So we've got a standard soil. We know how much phosphorus is in it, what the pH is. And if those results from that come back and they're not exactly where they're meant to be, we know something's off. So our analysis of soils is very accurate. We have a lot of quality controls in there. All soil testing labs do. So if there's a problem in the lab, it's caught very, very quickly. So again, the lab's very good at analyzing and getting the same numbers all the time. The real errors in soil testing come with the sample collection. I'm going to talk about pH a little bit. Water pH, it tells us the current pH of the soil. In other words, what the plant is experiencing. What is the pH of the soil? But does it tell us how much lime we need to apply? I mean, does a sandy soil need as much lime as a heavy clay soil? No. So what do? We've got what we call this buffer pH. This was instituted about 15 years ago at Virginia Tech, and we called it buffer pH, and then people would get confused because they'd look at their soil test report and there'd be a water pH and a buffer pH, and they're saying, why has my soil got two pHs? So we just changed it to a buffer index because the soil pH is where the soil's at. The buffer index, or the buffer pH, it just tells you how much lime you need to apply. It doesn't tell you what the actual pH of the soil is. So the buffer pH, we generate that with a buffer solution. At Virginia Tech, we use the Malick buffer, but there are a lot of different buffers out there. It doesn't matter which one you use. They'll each do an equally good job. You just need to make sure you use the same buffer with the same recommendation, because the buffers are slightly different. And again, it's got all of these different things in there. You don't need to remember what they are, but I highlighted a couple here. Ammonium, it's got a positive charge. Barium, positive charge. Oh, it's also got sodium. So it's got cations, and what they do is they kick the acidity off the soil. So in a soil, some of the acidity is in the solution, but a lot of it's held on the cation exchange capacity. So what these buffers do with these cations, they kick the acidity off the soil into the solution where it can be measured. Because the lime, when you apply lime, it needs to not just neutralize the soil solution, it needs to neutralize the acidity that's held on the cation exchange capacity. So this is a little schematic of two different soils. Out here in the coastal plain, this is what you've got, very low cation exchange capacity soils. Up here, this might be the Shenandoah Valley with a higher cation exchange capacity, heavier soil. So you can see, look how many negative charges they have. This sandy soil has only got a few negative charges. This heavier soil has a lot of negative charges. And you can see 50% base saturation. So 50% of these negative charges are holding base cations. So you've got your calcium, your potassium, maybe some magnesium, and 50% of it is covered with acidity. So this sandy soil, it's got a pH of 5.5, 50% base saturation. This high cation exchange capacity soil, much more negative charge, still 50% base saturation, same pH though, because it's got the same balance between how much of that cation exchange capacity is covered with cations versus acidity. So the pH of the soils is the same. Target pH for most of our crops is 6.2. That's where you want to lime to get a good crop. Buffer pH in this, we put the buffer. The buffer starts at a pH of 6.6, and the more acidity that's kicked off the cation exchange capacity, the more that pH drops. So this one has a buffer pH of 6.25, but look how much acidity needs to be kicked off this. So the buffer pH is only 6.1. So the water pH is exactly the same. The water pH shows that both soils have the same pH, but then you look at the buffer pH, and because there's more reserve acidity on the heavy soil, the buffer pH is going to be lower. And therefore, the lime recommendation is only half for this soil as it is for this soil. This is probably the thing we get the most questions about in the soil testing lab. I have 2 soil samples, the pH is the same, and you're recommending more lime for one than the other. And that's because the soil texture is different. There's more reserve acidity in one than the other. So it's going to take more lime to neutralize that reserve acidity in your heavier soil than in your sand soil. Any questions about that one? Buffer solutions, as I said, there are a whole bunch of different ones. In Virginia, we use the Malick one. There's the SMP, there's the Socorro, Woodruff, Adams Evans. There are a whole bunch of different ones. And all of them work effectively, but they all start at a slightly different pH. So they're going to end at a different pH. So you've got to use the right recommendations for the right buffer. So here's what our recommendations look like. Our Malick 1 buffer starts at 6.6, and after we added that buffer solution to the soil, if the pH comes back at 6.6, obviously there's no reserve acidity, don't need any lime. And then as the buffer pH starts to drop, you can see our lime recommendations go up. And it depends on the target pH. Again, for most of our crops, it's 6.2, so you're getting more and more lime recommended as your buffer pH drops. And we have lots of, this jumps, but we have it's much more refined. We go in half-ton, quarter-ton increments. Again, we've been over why do we need to collect a good sample. The scale-up factor, about 2 million pounds of soil per acre in a furrow slice down to your 6 inches. So 2 million pounds per acre, and if you take one sample from a 10-acre field, that's a lot of pounds of soil. So one soil sample, we're analyzing maybe 5 grams of soil from that, and there's a huge scale-up factor. So 2 million pounds, have any of you heard of the shortcut for PSNT? You'd think 2 million pounds, the concentration is parts per million, so you'd multiply by 2. For PSNT, pre-sidedress nitrate test, you take a deeper sample to about 1 foot. So PSNT, the rule of thumb is PSNT times 4 is your pounds per acre. So your PSNT comes back in parts per million. You multiply that by 4, you've got how many pounds of nitrogen you have per acre. Because it's 4 million pounds to that 12-inch furrow. Samples must be representative. How do you decide where to take a soil sample from? It's from one management unit, a minimum of 2 to 5 cores per acre, depending on how many acres. I mean, we really need at least 10 samples. I think different states may vary in that a little bit. And different states also have different recommendations. Generally, we don't want to go over about 20 acres. I think Virginia Tech says 10, but our nutrient management regulation says 20 acres. So the reason for this is how much variability you have. This doesn't look very much like the Eastern Shore, does it? But up in Virginia Tech, we get a lot of places like this. So you've got the flat bottomland, you've got a slope, maybe a lesser slope somewhere else. But you can see it when you take the soil samples. The soil samples down here are a lot darker, a lot more organic matter. The soils here can get eroded, and it's the smaller particles rich in organic matter that get transported further and end up down here. So, I mean, most of us deal with fields that are a little bit like this. If you're going to treat it as one unit, put your lime and fertilizer out as one unit, then you can sample it as one unit. If you can manage to split it up and treat it in 3 different units by soil type, that's better. But of course, that takes more time and effort. But precision nutrient management is doing more of that these days, and it's becoming more popular. Getting into the importance of soil sampling depth. This is a sample, top 2 inches is mostly organic matter. This is actually from turf. You see somebody put taper on this soil probe to make sure they're getting a consistent sampling depth. But this is in a turf situation where it's very organic at the top and it's mostly sand below that. So if, again, we asked how much can soil test vary one year to the next, this really shows you that if you've got a little bit of organic matter versus a little bit of sand. If you take a deeper sample, you're going to get more sand and be diluting that soil test. We talked about stratification of soil test phosphorus. So this is depth of soil versus soil test phosphorus concentration. Where you're applying phosphorus to a soil, it's going to be higher close to the surface. And then as you go down with depth, it's going to get less and less concentrated. So if we compare two different sampling depths, we have a shallow depth where we're sampling mostly the most concentrated phosphorus. And then we've got a deeper depth where you're diluting that a little bit with lower phosphorus soil. And this is the biggest reason for variability 1 year to the next in soil sampling, just not getting that consistent depth. Again, different labs doing different things, different units, different terminology. We've got easily extractable, and this is what they're calling Malic 3. Just depends on which lab and what they're calling it. This is our one at Virginia Tech. So we've got soil pH and we've got buffer index. Again, we used to call it buffer pH because it is a pH, but it just confused people. And that goes into our lime recommendations. Again, converting. Waters Lab, it's in Georgia. It's got pounds per acre times 5 equals Virginia Tech. So there are a lot of different ways to convert between soil testing, but if you're doing soil testing, it's better just to use the recommendations from that lab rather than try and do all of these conversions. Because the recommendations for that lab were developed for that soil test. Again, here's another different lab. Malic 1, it reports elementals. Sometimes you see pounds per acre, sometimes you see ppm. Again, a buffer pH of 7, so you know it's not the Malic 1 buffer that we use at Virginia Tech because it never goes above 6.6. So just use the recommendations developed for individual labs. How much time do I have left? I was just going to touch on 2 minutes. Okay, I'll go through this just quickly. Something on potassium. What potassium does in plants is it controls opening and closing of your stomata, so it helps the plants breathe. So here's a leaf in a plant. You can see these little stomata here. That's how carbon dioxide gets in, moisture gets out. And they open and close these to control gas flow and moisture. So should I fertilize with potassium? This is another question we get. My soil test level for potassium is high, but a fertilizer is still recommended to get into the very high range. Can I skip the application, or if it's in medium, should I go to high? How much yield will I lose if I skimp on the potassium a little bit? Well, the answer is it depends on the weather. And also remember, recommendations assume that soil testing isn't ever done every year. So if you're relying on a soil test from 3 years ago, it might not, your potassium may have dropped a little bit since then. But there's some work out of the Midwest. So rainfall amount, low, medium, high. And look at the yield for low versus high soil testing and potassium. For the medium, rainfall amount, it didn't matter if you were low in potassium or high. There wasn't much difference in yield. There was only an 8 bushel difference. But when rainfall was low, in other words, was drought stressed, potassium really helps with your drought stress. So you can see a huge yield response, about 39 bushels per acre. And again, when there was very high rainfall, they were, again, water stressed through too much moisture. Being able to control those stomata a little bit better, they were able to increase their yield. So this is some of the things we deal with in soil testing. We're looking for that one number, right? One number, we have enough potassium, but then the environment throws us curveballs. Again, this is out of Indiana. Ohio, the same thing. Low rainfall amount, you get a yield response. Medium, not nearly as much of a yield response. So I could keep going all day, but I think we'll stop there.